What specific problem does MiniMax-M1 aim to solve in the context of large reasoning models, and how does it differ from existing models like DeepSeek R1?
MiniMax-M1 aims to address the challenge of efficiently scaling reasoning lengths in large reasoning models, LRMs, while overcoming the computational limitations posed by traditional transformer architectures, particularly the quadratic complexity of the softmax attention mechanism. Unlike existing models such as DeepSeek R1, which still rely on traditional attention designs, MiniMax-M1 employs a hybrid mixture of experts, MO, architecture combined with lightning attention, allowing it to support a context length of up to 1 million tokens, significantly surpassing DeepSeek R1's capabilities. Additionally, MiniMax-M1 achieves a substantial reduction in computational cost, consuming less than 50% of the flops compared to DeepSeek R1 at a generation length of 64K tokens, making it more efficient during inference and large-scale reinforcement learning (RL) training. The model also incorporates a novel RL algorithm, CISPO, which enhances training efficiency by avoiding the clipping of important tokens, a limitation observed in existing models. Overall, MiniMax-M1's design and innovations position it as a more scalable and efficient solution for complex reasoning tasks compared to its predecessors.
How does the proposed MiniMax-M1 algorithm work? Illustrate its methodology step by step, particularly focusing on the hybrid mixture of experts architecture and the lightning attention mechanism.
The MiniMax-M1 algorithm operates through a hybrid mixture of experts, MO architecture, combined with a lightning attention mechanism. First, it begins with continual pre-training of the MiniMax Text O1 model on a large corpus of 7.5 trillion tokens to enhance its reasoning capabilities. Following this, a supervised fine-tuning SFT phase is conducted to instill specific chain-of-thought COT patterns, which prepares the model for efficient reinforcement learning (RL). The architecture features a transformer block with traditional softmax attention after every 7 transformer blocks utilizing lightning attention, allowing for efficient scaling of reasoning lengths to hundreds of thousands of tokens. This design significantly reduces computational costs, enabling MiniMax-M1 to handle long contexts of up to 1 million tokens while maintaining performance, as evidenced by its ability to consume less than 50% of the flops compared to other models at a generation length of 64K tokens.
Can you provide a simple yet illustrative example of how MiniMax-M1 operates during the reasoning process and how it would handle a specific problem? Walk through the algorithm's steps with this example.
To illustrate how MiniMax-M1 operates during the reasoning process, consider a mathematical problem such as solving a complex equation. The model begins by leveraging its hybrid mixture of experts, MO, architecture and lightning attention to process the input, which allows it to handle long contexts of up to 1 million tokens efficiently. Initially, MiniMax-M1 undergoes continual pre-training on a diverse dataset, including 7.5 trillion tokens, to enhance its reasoning capabilities. When presented with the equation, the model utilizes its supervised fine-tuning SFT phase to apply chain-of-thought COT reasoning patterns, breaking down the problem into manageable steps. As it generates responses, MiniMax-M1 employs the CISPO reinforcement learning algorithm, which stabilizes training by clipping important sampling weights, ensuring that all tokens contribute to the reasoning process. This allows the model to maintain coherence and depth in its reasoning, even as it generates lengthy outputs. For example, if the model encounters a reflective token like AHA, it retains this token in its updates, which is crucial for stabilizing the reasoning path. Ultimately, MiniMax-M1's architecture and training methodologies enable it to produce a well-reasoned solution to the equation, demonstrating its advanced capabilities in handling complex reasoning tasks.
What theoretical or practical benefits does MiniMax-M1 offer over traditional large reasoning models, especially in terms of efficiency and handling longer contexts during reasoning?
MiniMax-M1 offers significant theoretical and practical benefits over traditional large reasoning models, LRMs, by utilizing a hybrid mixture of experts, MO, architecture and lightning attention, which allows for efficient scaling of reasoning lengths to hundreds of thousands of tokens. This design results in a substantial reduction in computational costs, as MiniMax-M1 consumes less than 50% of the flops compared to DeepSeek R1 at a generation length of 64K tokens, and approximately 25% at 100K tokens. Additionally, MiniMax-M1 supports a context length of up to 1 million tokens, which is 8 times greater than DeepSeek R1, enabling it to effectively process long inputs and generate extended reasoning. The model's efficient reinforcement learning (RL) framework, particularly through the novel CISPO algorithm, enhances training efficiency and stability, allowing for a full RL run within 3 weeks using 512 GPUs. Overall, these advancements make MiniMax-M1 particularly well suited for complex, real-world tasks that require extensive reasoning capabilities.
How is MiniMax-M1 validated or tested? Discuss the experimental design, datasets used, and performance metrics that demonstrate the effectiveness of the method.
MiniMax-M1 is validated through a comprehensive evaluation across various domains, including mathematics, general coding, software engineering, reasoning and knowledge, long context, agentic tool use, factuality, and general assistant ability. The experimental design involves utilizing multiple benchmarks, such as Math 500 and AMY 2024 for mathematical reasoning, Live Code Bench and Full Stack Bench for coding, and SWE Bench verified for software engineering tasks. The datasets are meticulously curated, with mathematical problems sourced from competitions, logical reasoning tasks synthesized through a dedicated framework, and software engineering challenges derived from real-world GitHub issues. Performance metrics include average pass rates across sampled responses, with MiniMax-M1 to 80K achieving notable scores like 86.0% on AMY 2024, ranking it second among open-weight models. Additionally, the model's ability to handle long context tasks is highlighted by its superior performance compared to other models, demonstrating the effectiveness of its design and training methodology.
What limitations or drawbacks does MiniMax-M1 present according to the findings in the paper, particularly regarding its architecture and RL training process?
The MiniMax-M1 model presents several limitations and drawbacks, particularly related to its hybrid architecture and reinforcement learning (RL) training process. One significant issue is the precision mismatch between training and inference kernels, which hindered reward growth during RL training, necessitating adjustments to increase the precision of the output layer to FP32. Additionally, the model faced challenges with the GRPO algorithm, which adversely affected training performance by clipping important tokens associated with reflective behaviors, thus preventing effective long chain of thought reasoning. The RL training process also encountered instability due to the imbalance in negative and positive sample gradients, leading to pattern collapse and incoherent text generation. Furthermore, the model's reliance on a complex hybrid architecture introduced difficulties in scaling RL effectively, requiring targeted solutions to stabilize training and ensure efficient learning.